Hello and welcome to WJE's laboratories here in the Chicago, Illinois area of the United States. I am Arnie Johnson and I'm here with my colleague Mohammed Al-Batnoni in our vibration laboratory. We're here today to demonstrate for you the equipment that we use during vibration monitoring at museum construction projects. This demonstration is a supplement to the lecture that we gave in Amersfoort, Netherlands at the conference sponsored by Dr. Bill Way on vibrations in collections and transport. We titled our lecture Vibrations During Museum Construction, but with the subtitle Theme and Variations on the Three-Legged Stool Opus 2023 because we know that there is a full theme of vibration control that we can use at museums, but we need to allow for many case-specific variations on that theme to address the needs of each particular museum. And this is the analogy of the three-legged stool. We're trying to support all the goals that we need at a museum during a construction project, which are to protect the collection, to give guidance to the contractor, and then to enforce limits that protect the collection throughout the construction project. The process follows the timeline of the construction, before construction, right at the start, and then during construction. So before construction, we typically do some pre-construction testing and write a vibration control specification. And then right at the start of construction, we often do vibration trials in cooperation with the contractor and his means and methods submittals. And then during construction, and that's when we monitor the vibrations throughout the construction process with alarms and notifications to protect the collection in the event of any excessive vibration levels. That final step during construction is much more effective if we've done the previous two steps, the pre-construction testing and the trials. In our full methodology, we use a safe line concept. We all know that if we drop a pebble in a pond, the waves radiate radial from the source, and they typically lessen with distance, right? Now, imagine that the pebble is actually a piece of construction equipment, and those vibration waves eventually reach a collection of artworks. What we do in our method is we draw a line in front of the collection, and we call that the safe line. And along that line, we place vibration monitors, which we're going to demonstrate for you here today. Those monitors are set to a safe threshold for vibrations to protect the collection. So the art behind the safe line receives less vibrations and is protected, whereas art in front of the safe line would need to be deinstalled. So here's a real life example of how we've implemented that safe line concept at a real museum construction project. I love this photograph. Crazy. They dug a parking garage right next to the St. Louis Art Museum, and we did our pre-construction testing. Based on that testing, we then established a safe line within the museum. So in front of the safe line, they deinstalled artwork that was sensitive to vibration, and then behind the safe line, the galleries remained open and sensitive artwork was protected. Along the safe line, we then installed a system of vibration monitors, which we're going to demonstrate for you here today. The contractor was given guidance based on the pre-construction testing, and that project went very smoothly and very well. This shows the Noy Gallery in New York City, where they were doing roof construction and had very important galleries at the lower levels of the buildings. Here we did some limited pre-construction testing, gave guidance to the contractor, and then installed a vibration monitoring system, in this case, an accelerometer-based system around that beautiful Adele Bloch-Bauer Woman in Gold painting. We have three vibration monitoring systems we're going to show you here today. First of all, a wired accelerometer system that we installed in a beautiful showcase loaned to us by the Art Institute of Chicago. And then we'll show you a wireless accelerometer system, also in a showcase. And finally, we'll show you our Sigicom seismograph system, which is the most common system that we're using during museum construction.
So as Arnie mentioned, the first system we're going to demonstrate is our wired accelerometer system. So we have an array of different accelerometers of different shapes and sizes, and we use these to record vibration data during our museum work. These accelerometers do need a wire to be connected to a data acquisition system to record the data and process it and store it. So right here in my hand is one of our National Instrument Data Acquisition Systems. This one is called the Compact DAC. So the data acquisition system port itself is what I have down here, and you can connect these cords into that data acquisition system, and each of the cords can record up to 4 accelerometer channels. So for that system, we have 4 cords, so that gives us 16 channels. We do have single and triaxial accelerometers. Triaxial accelerometers are basically able to measure vibration in all 3 directions at the same time. This data acquisition system does need a laptop in order to process and store the data. Another version for our data acquisition system is another National Instrument equipment, and we call it the C-RIO. The C-RIO has a processor in it, so it has the laptop part already integrated as part of the same data acquisition system. And this one we usually use when we do remote monitoring, similar to the Noise Gallery project that Arnie mentioned. Again, you need to connect the cords in each of the C-RIOs to collect the data. But once we have the data collected, processed, we can then transfer it remotely to our WGE servers in Chicago, Illinois.
The second system we want to show you is our wireless accelerometer system that we have installed here. These small nodes by Lord Parker Microstrain G-Link 200 are what we're currently piloting. We have some other wireless options as well. They operate on these very small and expensive lithium batteries that honestly don't last very long. One of the limitations is the battery life of these wireless nodes. The other limitation is that they have to connect to a gateway. The distance of the nodes from the gateway is a limitation, line of sight, a few hundred feet perhaps maximum without barriers in between. But this is a new system that provides some flexibility. We don't have all the wires strung through the galleries.
So the third system that we're going to demonstrate is our seismograph system. So these here are SIGCOM seismographs. The unit in my hand is called the C12 unit. We also have another unit that's called a C22 unit. Both of these units are part of our seismograph inventory, which include over 200 seismographs that are distributed around the United States to do monitoring in many buildings and museums around the nation. These systems are what we call a 3-in-1 systems. They are standalone instruments that are capable of recording the vibrations, processing and storing the data, and transferring it back to our WGE servers. Each of these units contain a velocity transducer that will measure the vibrations in terms of inches per second or millimeter per second, which what we use to compare to our vibration limits. We also have a data acquisition system in here, and the data acquisition system can process the data in real time and then transmit it with the cellular modem that's also included in here to our WGE servers. The main advantage of these systems, again, compared to accelerometers, is that they are standalone. However, our accelerometer wired systems are far more advanced in their capabilities to process and analyze the data in more ways than what we can think of. So now Arnie and I will show you how to use our wired accelerometer system to collect some vibration data on simulated artwork.
For this live vibration demonstration, we have instrumented the art case that was provided to us by the Art Institute of Chicago with 3 accelerometers. We have an accelerometer on the concrete slab below the case. We have a second accelerometer on the bottom of the case itself. And then on the platform of the case, we have a third accelerometer. All of these are wired into our data acquisition system, and we will now simulate some impacts and some chipping hammer work to generate some vibrations in these 3 accelerometers. All right, here's where the work gets fun. We've used a modal hammer to generate some simulated impacts. Now we're going to use a real piece of construction equipment, just a small chipping hammer, to generate some continuous vibrations into this art case. I'll be chipping on a block of wood so I don't damage the concrete, and I'll be chipping close to the case and then far away. And now a more short burst of transient vibrations. and then a shorter transient burst. So that was fun. That experiment generally showed us, as you saw on the screen, that vibrations were higher when we were impacting or chipping closer to the case and smaller when we were farther away. You also probably noticed that the vibrations on the concrete slab were higher than on the case and certainly than on the platform. With that, we're going to segue into demonstrating our seismograph system, which Mohammed will demonstrate.
This is a view of our vibration monitoring data portal where we can access the data from all of our seismographs that we have installed around the nation. As you zoom in, you can actually see more close-up of the actual location of each of the projects. You can click on a project, see the name of the project, where it is located, how many vibration monitors we have installed on the project, and who are the users that will get alerts or notifications from that project. You can also go ahead and create a data report. And from the data report, you can select whether a week, a day, or a specific time in the day. And you can open the report, see the data that's collected by each of the vibration monitors, zoom in, and see data collected at specific times. And if you have any trigger vibration events, you can open that trigger event and take a look at the waveform, which in this case, the example we're showing is a continuous waveform from a vibration triggered event. For each project, we can set up alerts and thresholds. So if the vibration levels exceed a certain threshold, we get a notification sent to the project team that could be either an email or a text message. The project team usually includes WJE, the client, and in some cases, the contractor. By reviewing the alert, we can make a determination whether construction can continue or construction should stop until we figure out why the vibration levels were exceeded. This allows us to provide the services for our clients in terms of earth protection and even in some cases to protect the building itself if it is a historic building.
All right, so that concludes our vibration demonstration here in our vibration laboratory. Thanks to you for attending, and thanks to Bill Way for organizing this tremendous workshop. We hope to see you soon.
Thank you, everyone.